we do the extremization of this action integral. Now, most of the equations of motion in nature, you can say, that is in classical mechanics, quantum mechanics, they have been derived from this principle of action, where the extremization is done. Okay, for example, let me give you examples how this principle of action, what this principle is, that I will tell you later. Let me give you some example. Extremization can be either minimization or the maximization, but in most of the cases it is minimization. So let me start with some examples. For example, if there is an object which is in the stable equilibrium, okay, what do we say? That is that its potential energy is minimized. Again, this is the principle of action. That is, you can say, this is the extremization you are doing of the potential energy function here. Okay, another examples we can take. Another example. Okay, let's come to statistical mechanics. In statistical mechanics, we have different thermodynamic system. Okay, if I'm taking a thermodynamic system which is in thermal equilibrium, then for the thermal equilibrium part, what do we say? That its entropy is, what happens to the increases? Entropy increases or entropy is maximized. This is again the extremization of the action integral. Another example I can take, we have for you must have heard about the Helmholtz energy function, right? Helmholtz energy function, which is given by U minus Ts, correct? Where U is the internal energy, T is the temperature, S is the entropy. This Helmholtz free energy, again minimization of Helmholtz free energy when the thermodynamic system is for which kind of thermodynamic system? For the constant volume and the constant temperature. Then we have Gibbs free energy again. Okay, so these are all the examples of this principle of action, which has been constantly used to find out the equations of motion. Now, these all examples I have taken, they are basically for the static system. So this is not just this principle of action is not just applicable for the static system, but we see it is also applicable for the dynamic system also, that we will see later on. Now, the question comes, what is this principle of action? This principle action, this principle of action is here for the Lagrangian formalism. I will be taking as the Hamiltonian principle. Hamiltonian principle. Okay, I'm just giving you brief right now. I will be starting with my slides later. The Hamiltonian principle, this is a kind of a variational principle which is used to find out the equations of motion. Here it will be used to derive the Lagrangian equation of motion. From that we will find out how the Newton's equation of motion, that is F is equals to ma, came into picture. Okay, so these are the examples. These are the dynamic systems which you all know about. First is a mass is moving down an inclined plane. This kind of a problem you must have all solved in your 10th and 12th. Okay, in mechanics, this is very important. How do you do that? You have to identify all the forces that are acting on this mass. For example, here I am neglecting the dissipative force, that is your frictional force here. Okay, this I'm neglecting here. Then what you will be doing? You will be equating. Okay, you can draw a free body diagram for this, and what you have to do is you have to point out all the forces that are acting on it. Then you equate, and using Newtonian mechanics, you find out the equation of motion. Okay. Now, this is the solution that you can, I will share my slides. You can see it later on. Another example of another system is, this is Atwood machine, where we have a pulley, heavy pulley, and an inextensible string holds two masses, M1 and M2. And then you are supposed to find out the acceleration here. Okay, this I'm giving you the examples of system that we will be dealing with after the Lagrangian formulation. Okay, then again we have a free body, a free object that is under the effect of gravity. Here I've included a retarding force also. Why I'm telling you? First, you try to do all these examples with the Newtonian mechanics. Then we will be looking at these very examples with the Lagrangian formulation. Okay. Now, what I will be doing is, we have seen the kind of systems that we will be dealing with right now. And now we will start with the derivation part. What derivation part? How to derive the Lagrangian equation of motion using the action principle. Principle of action, that is your action integral. Okay. Now let me write here the action integral. Action integral, it is given by S, T1, T2, T1, T2, L, Dt. This is the action integral for what? This is a coordinate. If I'm taking the phase diagram, and 2 points on this phase diagram. This is T1 at T1, this is at T2. We have a system. I'm taking a system which is at T1 here, and this is after some time T2. Now, which trajectory it can take? It can take any trajectory from here to here, or this, or this. This is a system. Okay. I'm talking about, and which kind of trajectory it can take according to the principle of action. Usually what we do here is basically the minimization. Extremization here is the minimization. So it is also known as the least action principle. It will not actually always be minimization. It can be maximization also. But for most of the equation of motion part, it is the minimization. That is why it is also known as least action principle. Least action principle. One second. Least action principle. Now, what this least action principle states, it states that the path the system will take from going from T1 to T2, it will be the path that takes the least amount of time. It will take the path where it will take the least amount of time. That is your least action principle. What we will be doing, we will be taking an integral S and we'll do the extremization of this action integral, and we will be finding out the equation of motion. This is one of the methods from which we can derive the Lagrange's equation of motion. Other than this, there are other methods also which can be used to derive the Lagrange's equation of motion. One of the other method is using the D'Alembert's principle. D'Alembert's principle is basically based on the principle of virtual work that I will not be discussing right now, but what I will be discussing is the least action principle. Okay, as discussed earlier, I was talking about the action integral we will be taking here. That is your S. And then I will be taking the extremization of this action integral. Extremization of this action integral, which is this. And I will be deriving the equation of motion, that is the Lagrange's equation of motion. Okay, so the Lagrange's equation is basically referred to as the Euler-Lagrange's equation that we will be deriving, which is, right now, let me just give you a view. D by dt del L by del Q I dot minus del L by del Q I equals to 0. Okay. First of all, let me tell you about this Lagrangian. This mechanics Lagrangian is basically a function, which is a function of the coordinate. This is known as the generalized coordinate Qi, generalized velocity Qi dot, and time. Now this Lagrangian equation of motion we will be obtaining, which is a function of Qi dot, and t. Now these are known as the generalized coordinate, generalized velocity. Now why I have introduced the words generalized? Generalized because it can take coordinates in any form. This is a general, for the simplicity you can say. Generalized coordinate, for example, it can take Cartesian coordinates, it can have spherical coordinates, it can have cylindrical coordinates. Okay, theta, you can take theta, you can take x, anything is included here, generalized coordinates. Now, the differentiation of the generalized coordinate gives you the generalized velocity. Similarly, we have a term generalized momentum also. Okay, the same thing. Now, why I have used the word I here, as you can say I here, because I am also introducing the degree of freedom here. Degree of freedom for any system, it will have a fixed degree of freedom. Mind you, here we will only be talking about for now the conservative systems, as well as the systems having fixed degree of freedom, all the finite degrees of freedom. Okay. Now, finite degrees of freedom, for the finite degrees of freedom, that means, and we have systems which have we have infinite degrees of freedom that are not to be taken here, just the finite degrees of freedom. Now, we all know what are degrees of freedom. Okay, for example, let me take a very simple example, which we discussed earlier, that is a mass going down an inclined plane. Mass going down an inclined plane, the degree of freedom, or the number of coordinates which can be used to perfectly define the system. In short form, you can say this is degree of freedom. For the inclined plane part, I can say there's just that is a typical example. Before that, I can take simple pendulum example. For the simple pendulum part, I just need to know the theta. Then I will be able to get each an information about the system. So theta here is the degree of freedom. Theta, that is just one coordinate is required. So the number of degrees of freedom for the simple pendulum system is 1, and the generalized coordinate will be theta. Okay, so this is about Qi dots, and I we take as the number of degrees of freedom, that is up to 1. Okay, so I was telling you about the Lagrangian, that is your L, which we will be deriving Lagrange's equation of motion, that is the Euler-Lagrange's equation of motion. As I was telling you, it is a function of generalized coordinate Qi, generalized velocity, in time. Okay, so I here represents the number of degree of freedom your system is having. So how will we proceed with the derivation? we will be using the Hamilton's principle. That is the principle of least action. As I was telling you earlier, it is a kind of a variation principle here. As L is a function of Qi dot, I can write my L in this way. Okay, L is a function of Qi. Okay, you can say Qk and Qk. Again, K represents your degrees of freedom. Qk dots. Now you plug in the value of L here, that is in the Hamilton's principle, and you will be getting this kind of a equation. Okay, now as you can see here, all I have done is I have plugged in the value of L in the Hamilton's principle. That is I am doing the extremization of the action integral, which will be equals to 0. Extremization. Here, the minimization basically. So you plug in the value and you solve this equation further by parts. I will be sharing the slide, so don't worry. You can go through the derivation part at your home. Now you plug in the value, you solve this equation by parts. How do you solve an integral by parts? The same thing. Taking first function, second function, this as your first function and this as your second function. Okay, now what do you get? This is what after optimization, plugging all the values and the rearrangement term, this is what you get in the end. Now this part, d by dt of del L by del Qk dot minus del L by del Qk is your Euler Lagrange equation of motion. Euler Lagrange equation of motion. Okay, we have derived the Euler Lagrange equation of motion. From this we will be deriving your Newton's equation of motion. Okay, okay, now how to derive the Newton's equation of motion? D by dt of del L by del Qk dot minus del L by del Qk is equals to 0. This is my Euler Lagrange equation of motion. Okay, or I can do the rearrangement, shift here, the same thing. Okay, now for deriving the Newton's equation of motion, what I will be doing, I will be taking, let me just take the example of a free particle. For free particle, what we will do is we will find out these terms and then find out what is your L, and then from that we will derive the Newton's equation of motion. Now what we do is we take that your L is T minus V. That is, it is having the dimensions of energy, where T is your kinetic energy and V is your potential energy. I have simply taken, we are doing the reverse part. I've simply taken that L is your T minus V. What we have seen is if we take L as equals to T minus V, we get the equations of motion. Okay, so this I have taken, L is equals to T minus V, and the system that I'm talking about is a free particle. For a free particle, what is your kinetic energy? For a free particle, your kinetic energy will be half m q k dot square. Okay, here you take as k all. K, let's just take just one degree of freedom, then K will be 1. Okay, we know that the kinetic energy for a free particle is given half mv square, where qk is nothing but your generalized velocity. So it will be half mk qk dot square. Okay, now qk dot square, then your potential energy will be what? Your potential energy will be what? Your potential energy will be, if I'm taking mg qk, this is your potential energy depending upon what is your reference point. Okay, mgh or it is your mgqk. Same thing, we have now L as equals to T minus V equals to half M K Q K dot square minus mg qk. This is qk, okay, just qk. Now since I've taken k, then you can take this as k as equals to 1 to n. Okay, now you find out, what do? Plug in the Lagrange's equation of motion, that is del L by del qk dot. What will you get here? You will be getting mk qk dot, correct? And then we have del L by del qk. What you will be getting here? Minus mg, correct? Then in the Euler-Lagrange's equation, plug in these values. You will be getting what was your d by we had obtained the Euler-Lagrange's equation, right? Till that part, I think everybody could hear me. Shall I move ahead? Okay, we had derived the Euler-Lagrange's equation. Now from that, I wanted to tell you how the Newton's equation of motion came into picture. Okay, so what I did, I was taking an example of a free particle. What I did was, I took this Lagrangian function, which was a function of qi dot and t, as t minus v. This is having the dimensions of energy, and it was given by T is your kinetic energy and V is your potential energy. Correct? This I'm taking my Lagrangian to be. It is obviously a function of generalized coordinate, generalized velocity and time. Now, taking a case of free object, your T will be given by I equals to 1 till n half mi vi, or you can say qi dot square. This is your T, whereas your V will be a function of q1, q2, qn, so on. This will be your V. Now your L will be T minus V. Now using the Euler-Lagrange's equation, del L by del qi dot equals to del L by del qi. Plugging in the values of T and V here, what do we get? Your del L by del qi dot will be your what? Will be minus del V by del qi. Correct? We know that this expression is minus of grad V is what? It represents force, conservative force. This is important. Again, this I told you earlier, we are only talking about the conservative systems right now, not the non-conservatives one. So on the left hand side, this will be given by mi qi dot dot. So F is equals to m. This is your generalized acceleration, ma. which is nothing but your Newton's equation of motion. So from the action integral, principle of action, we have obtained Euler-Lagrange's equation and the Newton's equation of motion. Is it correct? Now, after this, what I want to discuss is what are the advantages of the transition from the Newtonian mechanics to the Lagrangian mechanics. Okay, first advantage that we will be looking at is your Lagrangian is a scalar, quantity. Now, what is a scalar quantity? We know what is a scalar quantity, something that is which is not dependent on the direction. This we all know. This is a general definition we know of the scalar. It is not dependent on the direction, only the magnitude. That is your scalar. However, the kind of scalar I am looking at here is the scalar quantity which is invariant under Lorentz transformation. This is how you will be taking your L as scalar here. Something which does not shift, does not change under Lorentz transformation. Okay, this is your first advantage. Now moving to the second advantage. Second advantage of Lagrangian mechanics is it automatically takes care of the constraints or the forces of constraints which exist in nature. We need not to know about the forces of constraint which are acting on the system right now. As I was telling you earlier, in the example that I took of the inclined plane, what did I tell you? For the free body diagram, how do you start with the Newtonian mechanics? First, you identify all the forces that are acting on the body, on the system. This is the first thing for the Newtonian mechanics. However, for the Lagrangian mechanics, you only need to know about the generalized coordinates of the system. What are the degrees of freedom? And then the kinetic energy and the potential energy. That is all. Everything is taken care in terms of the degrees of freedom and the generalized coordinate. Okay. So that is your second advantage. Now, what is your third advantage? Your third advantage is in the relativistic mechanics, in the special relativity also. Okay, where your Newton's laws, they fail. They don't apply. What we do there in relativistic mechanics, we can use Lagrangian mechanics there. Okay, that is one more advantage. Now, other advantages are where we are talking about the degrees of freedom which are not discrete but continuous degrees of freedom. In that case, also that is in the field theory. There also we use Lagrangian mechanics. Okay, so Maxwell's electromagnetic equations, they were derived from a tensor Lagrangian that was taken. Okay, I'm not going into deep, but these are all the advantages that I'm discussing. So everything has an advantage as well as disadvantage. What are the disadvantages of Lagrangian mechanics? First disadvantage is that you cannot solve this for the quantized system. Quantization is not possible in case of Lagrangian mechanics. So what was done? Hamiltonian mechanics was introduced. We use a that is in quantum mechanical system. You all know how do you solve the quantized system using Hamiltonian mechanics. Okay. Second disadvantage is this Euler-Lagrangian equation is a second order differential equation, which is difficult to solve. Okay, it would have been much better if we have a first order differential equation. So again, a shift was from Lagrangian mechanics to Hamiltonian mechanics, which has the advantage of having first order differential equation. Okay, these are some of the disadvantages of Lagrangian mechanics. Now, this I have tried my best to explain it to you, how the Lagrangian mechanics was, how the Lagrange's equation of motion was obtained, and from the action principle, and from that how the Newtonian equation of motion came into picture, and then the advantages, disadvantages of the Lagrangian mechanics. I was not able to solve the questions using Lagrangian mechanics. That I will try to do tomorrow, okay, as I do not have time right now. So that is all for today's lecture. Any questions right now? Or I will conclude.
Yes, ma'am. We have some more.
Okay,
there's
Aziz,
a small question.
Yes, yes.
While informally introducing Hamilton's principle,
You're not
said that
audible
the
to
path
me.
of
Hello? Yes.
a physical system goes through phase space.
We have taken phase space right now. Yes.
That was my doubt. Whether it is. Am I audible now?
Yes, you're audible.
My doubt was whether the path is through phase. Oh, okay.
Yes, yes. Go on. Okay.
Hello.
Chat. Yes.
Yeah, my doubt is whether the path is through a phase space or is it through a configuration space?
Okay. Right now I have taken through a phase space. That is why your Lagrangian is a function of the generalized coordinate and the generalized velocity.
Okay, that was my doubt, because I had a question. I had a doubt reading somewhere. Some places I thought it said configuration space, and some places it said phase space. So that was a confusion.
Okay, no. We have taken the phase space here. That is why the independent coordinates here are the generalized velocity and generalized coordinate. Okay, it is only depending on these.
Okay, ma'am. Thank you.
Okay. Yes. Any other question? See, if you have questions regarding today's lecture, you can ask tomorrow also. Okay. I will be coming tomorrow. We will start with the problems. Then I will start with the Hamiltonian mechanics. Why a shift from Lagrangian mechanics to the Hamiltonian mechanics was done. Shall I conclude, sir?
Yes, madam.
I hope you people enjoyed this lecture.
If there are no more questions, then we would like to thank Dr. Sheetal for today's lecture. We'll meet again tomorrow. Thank you, madam.
Yes. I hope you enjoyed and you learned something today.
Yeah, thank you, madam. Yes, madam. Thank you very much. If there are no more questions, we'll see you again tomorrow.